Hello, I'm Dr. James Dborin and I am the Head of Research at DoubleWord AI, and today we are continuing our series on advanced topics in self-hosting LLMs with the video titled How Many Users Can My GPU Serve? And in our mind map of topics in self-hosting LLMs, we're going to be covering the topics of inference engine configuration and then core components like hardware selection, model selection, and inference engines. So at the end of this video, we're going to hopefully have covered three tasks. One, we want to understand the KV cache and be able to calculate the size of the KV cache. This will be useful in answering the question of the video. Two, we want to be able to use the size of the KV cache to estimate the users and context length that can be served by my model. And three, we want to understand how we can increase this number, so serve more users or serve a larger context length. So let's get started with that first point. So we want to understand what the KV cache is and how to size it. So starting with what the KV cache is, I'm going to draw the KV cache as a big box. I've done this in other videos we have, but the KV cache is a big chunk of memory that we allocate, and we have slots in it. I'm going to draw this as a 2D chunk, and each slot represents one token. So I can represent the sort of fullness of a KV cache by saying maybe these slots are taken up by this user's request, this orange user's request, and then this blue user has used 3 tokens. Maybe they had 2 tokens in their request, and then the model has generated 1 token. Each token takes up a single slot in the KV cache, ignoring things like reusing bits of the KV cache, which is a sort of more advanced topic that we've spoken about in other videos. So the KV cache stores the user's tokens as 1 slot per token. And what we want to know is how many tokens in total can be stored by the KV cache given my model choice and GPU choice. So we pre-allocate this KV cache in a single chunk of memory, and we pre-allocate it and we know the size it's going to take up. It's going to take up the following size. So the KV cache size, measured in gigabytes, is equal to the GPU's VRAM minus the size of the model weights, and then minus again the model activation. So the activations are memory that has to get allocated during the forward pass of the model. During the prefill stage, it can store quite large tensors, and we have to pre-allocate those as well, or at least leave space for them behind. If your inference engine is doing something like chunked prefills, you can control the size of these activations, and they tend to be a lot smaller than the size of the KV cache of the model weights. So for this video, we're going to ignore them. In practice, your inference engine should be sort of keep managing this for you and making sure it's smaller, and this is often a configuration variable, the chunked prefilling size, if you're using something like VLM or the DoubleWord inference engine or something like that. So we're going to ignore this for now, but note that in reality, there's small changes in this calculation based on these activations. But as a sort of rough guide to how many users you can serve, we can ignore it. So for example, if we're serving like a Llama 8B, and we're serving it in 16-bit precision, either FP16 or BF16, then this will take up 16 gigabytes of space, 2 bytes per parameter. 8 billion parameters is 16 gigabytes. And let's say we're serving it on a single A100, which has 80 gigabytes of VRAM. We can say that the KV cache is approximately going to take up 64 gigabytes of VRAM. Again, ignoring the activations to avoid overflow, to avoid out-of-memory issues, you might make it slightly smaller. Most inference engines have an option to make it 90% as big, 80% as big as this value, to avoid out of memory errors. So maybe in practice you'll end up with 60 gigabytes or 55 gigabytes, but we'll move forward with this, this value for now. So we have this value. We know the KV cache is going to take up 64 gigabytes of VRAM on my GPU. So now we need to know how many tokens that equates to. So we want to be able to calculate the number of tokens that can be stored in my KV cache, and this will be equal to the KV cache size, again measured in gigabytes, and then we're going to divide it by the gigabytes per token. So each token is going to take up a certain amount of space in the KV cache. Each one of these tokens, each one of these slots has a total amount of space, and we can calculate that. And so we're going to do that here. I'm going to walk through what that calculation looks like. The gigabytes per token is equal to, if you're using a model like Llama, which has a different number of attention heads and key value attention heads, you need the number of KV heads. So for example, for Llama 8B, this is 8. You need to multiply by the dimension, the head DIM size. So each one of these tokens has, each one of these heads represents a sort of vector, and we need the size of that vector. You need 2 copies of this, one for K, one for V. You store both of these. You store a K and a V for every layer. So you take the number of layers in the model. And then if you're storing it in 16-bit precision, which is the most common, you're going to multiply this by 2 bytes per floating point value. If you quantize the KV cache, which we'll talk about in a bit, this number will change. And then finally, you divide all this by 10 to the 9 to get the gigabytes per token. If I do this for the Llama 8B, and you plug in these numbers can all be found on like the Hugging Face config page for the model. It doesn't quote the head size, but you can work that out by the hidden size and the number of attention heads. And I get approximately 0.00013 gigabytes per token. And so this is good because now I can use this directly to calculate the number of tokens that can be stored in my system. So I had 64 gigabytes of KV cache space, and I have 0.00013 gigabytes per token. And so the number of tokens is approximately equal to 400,000 tokens. So that means that simultaneously on my GPU, I can be processing 400,000 tokens at any one time. I can be storing 400,000 tokens. So this is in total between the pre-filled tokens and the generated tokens from the model. So this doesn't quite answer the question, how many users can I serve? But we're close. So if I want to know how many users I can serve, I need to have an estimate of the number of tokens each user is going to need processed. So finally, the number of users is equal to the total tokens that can be stored divided by the token per user. So for example, let's say you are working with a sort of RAG model, and the RAG model is going to require 8,000 tokens of context in order to answer its question, and then you expect it to generate something like 2,000 tokens in every answer. Maybe that includes thinking tokens, maybe it just includes the tokens for the user if they want to generate quite long paragraphs. And so I can say that the number of users that my system can handle if I'm serving a Llama 8B on a single 80 gigabyte A100 is about 400,000 divided by 10,000 tokens per user which is about 40 users in total. So this can obviously go up if your users are sending shorter requests than you expect, or the model is or the model is responding with shorter responses than you expected. It can go down if the model is answering with longer responses, or more than 8,000 tokens are getting processed by your users. But this is a good rule of thumb, back of the envelope way to estimate the number of users that can be supported on your given setup. So things that we are not taking into account here. There's a few things we're not really taking into account. One such thing, obviously, like I spoke before, is the activations. So this might be lower because of the activations. Another thing we're not talking about is page sizes. So if your inference engine is using page attention, it divides the KV cache into pages of 256 tokens is a common one. And so you can only allocate memory in chunks of 256. And so in practice, you might end up with some fragmentation. That means this is you can support slightly fewer users. If you're not using page attention, you're using normal flash attention, kernels that aren't paged, then you might end up with lots of fragmentation that might be much lower than this. In that case, you define ahead of time the number of users you want to support, doing a similar calculation, but it's not as flexible as this. You can't dynamically scale up the number of users by changing the context length. And we're not taking into account various other tips and tricks that might be useful in increasing or decreasing this size, like things like KV cache quantization. Okay, so we've now seen roughly how to estimate the number of users you can support. So let's take a look at ways that we can try and change this. We've sized out our system. We've seen that we can support 40 users at 10,000 tokens a user, and we've decided this isn't enough. We need to support more than 40 users. We need to support 40 users but with longer context lengths, or we need to support a single user with more than 400,000 context length. I have a model that can reason over that distance, but my GPUs won't allow me. So let's look at how we can increase this value. So we'll go back to the original formula that we had, which is GPU VRAM minus model weights. And then finally we had number of tokens is equal to KV cache size divided by gigabytes per token. So these are the sort of two key equations that we have the ability to manipulate in order to try and change the number of tokens we can serve. So we don't actually have a lot of things we can do here. There's a few things we can do. Quite obviously, just looking at this formula, what we can do is we can try and increase the GPU VRAM. We can try and decrease the size of the model weights, and we can try and decrease the number of gigabytes per token. So with the model weights, we can do something like quantization. We said that the model weights were approximately 2 gigabytes per billion params, and that's if you serve it in 16-bit. If you serve it in 8-bit, then you only take up 1 gigabyte per billion params. If you serve it in 4-bit, you take up half a gigabyte per billion params. And if you go to something extreme like 2-bit quantization, you take up 0.25 gigabytes per billion parameters. So if I do something like 4-bit with the Llama 8B now, rather than taking up 16 gigabytes, I take up 4 gigabytes of space, and this gives me an additional 12 gigabytes left of KV cache size to play with. And as you see, like each token doesn't take up a lot of space, and so that's sort of tens of thousands of more tokens that I can now play with. That's sort of additional users. And you can see how this will be really useful if you're serving very, very large models. The other thing we can do is try and increase the GPU VRAM. You could imagine vertically scaling your instance. If I'm serving on an L4 with 24 gigabytes of VRAM, I can increase the number of users I can serve as well as the number of as well as the context length I can serve by going up to an 80 gigabyte A100 or a sort of 128 gigabyte setup with the most modern GPUs that are being released. But once I hit that limit of what is available in a single GPU, I can no longer vertically scale. So you can horizontally scale instead. If I get a node of GPUs, each with 80 gigabytes, let's say. So I have 8 GPUs, 8 sets of GPUs, 80 gigabytes in total. This gives me a total of 640 gigabytes of VRAM to play with within the node. And I can split a single model over that node. You can use a technique like tensor parallelism to effectively partition a model across a node, and it will act in some ways as though it's one model on a single GPU of 640 gigabytes of VRAM. And so when you can't vertically scale your GPUs anymore, you can horizontally scale them within a node using something like tensor parallelism, and then even across nodes using something like pipeline parallelism or otherwise. So you can keep increasing the size of the effective VRAM that you operate with and increasing this number here to increase the size of the KV cache using various forms of parallelism to split your model across GPUs and across nodes. Depending exactly on the inference engine you use, this splitting is more or less efficient. Some weights get duplicated across GPUs, some get split. And so it doesn't exactly work out that if I double my VRAM, that I double the KV cache size, but approximately it does. And so if you need to go to higher and higher KV cache sizes, you can do that by splitting the model across more GPUs and then across nodes as well. And then finally, the last tool I have available to me is to try and decrease the gigabytes per token that gets stored on GPU VRAM. This is sort of more experimental. It's a bit harder to find in inference engines, but this is things like KV cache quantization. So similar to model quantization, rather than storing my KV cache in 16-bit, I can store it in 8-bit or 4-bit or 2-bit or something like that. And every time I do that, I get a multiple number of tokens increase. So if I go from 16-bit to 8-bit, I effectively double the number of tokens that I can store on my GPU. This can have some latency concerns. There can be latency issues with this if you aren't using attention kernels that fuse the dequantization of this for you. So there's something to be concerned about. You can do something else, like you could do an offloading strategy. You can store your KV cache off of the GPU and only have 1 or 2 layers on the GPU for the sort of next layer. And so rather than having 32 layers worth of KV cache stored on the GPU, you store 3 layers worth of KV cache. You get a 90% reduction in the size of the KV cache stored. And so in principle, you could process 10 times as many tokens at the same time. In practice, this is a bit hard. It's not always perfectly overlapped with computation, like moving the KV cache weights on and off the GPU. And so you might find, again, there's a latency issue with doing this, but this is a nice strategy for to increase the number of tokens that you use without impacting the model quality at all, like the KV cache quantization might. That does change the model quality. But it sort of depends whether your inference engine supports that sort of thing. Okay, so there we have it. We've seen now how to calculate the size of the KV cache using information from the model's config and information from your GPUs. Given the size of a KV cache and information from a model, we can estimate the number of users that we can support and the context length we can support. And we see that there's a trade-off. More users means shorter context length, longer context length means fewer users. And then finally, we looked at 3 ways that we can increase this. We looked at ways to increase the GPU VRAM via parallelism strategies. We looked at ways to decrease the size of the model weights like quantization, and then more experimental techniques of decreasing the number of gigabytes that each token takes up.